So last week we have been talking about the PM motor, permanent magnet PM motors. So we just continue with them. Yeah. So key thing we like to develop the permanent PM motor because we can turn the motor inside out. In this case, the wiring we can connect from the stator side, and the rotor will become a PM. So in this case, like in this motor, then the winding are putting outside in here. So all the wiring can connect to the stator, which is not going to rotate. And then internally here will be our PM permanent magnet. The permanent magnet will stick on the rotor. In this case, we don't need any wiring connection. So that makes the configuration much simple. So this technique, we call it turn the motor inside out. In this case, we are able to have the motor without the use of the commutator and carbon brushes. So that's one of the simple configuration, but we're able to change so much connection for the motor. So brushless DC is one of the advanced development mainly because in the past we used mechanical method to do the changing of the current, but now we can use power electronics to change the current. So by using power electronic solution, we can just using a Hall effect sensor or other sensor, positional sensor, to sense location for the motor, where you rotate to, where the B field will appear on which angle, and then we energize the corresponding winding. In this case, it's just the same as the conventional DC motor. So that means this kind of brushless DC, we do need to have a position sensor, like Hall effect sensor. So, the synchronization will be important because rotor position must be synchronized with the winding. So we need to switch the corresponding winding to do the job. So this is the motor which can able to replace all the mechanical commutator using power electronics. That's what we're trying to do. So this motor, you can see that the stator only with the copper winding. So in this case, the wiring connection will be simple. And sometimes the cooling can also be simpler because the winding usually will be conduction losses, eddy current losses. In this case, all the winding will be outside. So that will make the thing much easier. The other motor, like the conventional DC motor, the winding will be internal. So that means the heat dissipation also be quite complicated. So here will be one of the basic topology for the brushless DC motor. So for instance, we got three sets of winding, we call it three phases. Each phase will connect to the two transistors. These two transistors, we usually call them inverter link or other names. So this one of the item here, we call it inverter link. So there's many different name. So this inverter link able to connect to the winding. So the connection here, there will be three winding. So this three winding, we can connect in either delta or star. So for these networks, we tend to use the Y connection, the star connection to show you how they're putting together for the three winding. So this motor is exactly the same as the other DC motor. We also have the back EMF. So later I will show you how the back EMF look like. The back EMFs appear when we have rotation. That means the change of the magnetic flux. And then we also need a PM. So that means when we have PM, we also have rotation. Then we should be able to see the back EMF. Later I will show you how the back EMF look like, the back EMF look like. So we try to locate the permanent magnet in roughly about 120 degrees in that particular location. So for my design here, so that's here will be the PM. So since in here, I just cover about 120 degrees. Of course, there's many other design you can use it, 120. So this 60, we have nothing there. So this 60 degree empty of the PM, we allow the PM to change over from North Pole to South Pole. And then we also give a rest to some of the winding because every time we only turn on two sets of the winding. The other one set of winding will not contribute to any torque. So in this case, we can empty the PM And then in this case, we are able to only operate on 2 sets of the winding. That's how my configuration is. So the current, we need to energize the current because we don't need to turn on the motor winding 360 degrees. We only turn on the two-thirds. So we can see here 120, 120. So we only each time only 2/3 of the winding are being energized. So the other 1/3 don't need to do anything. So in this case, you can see that the waveform, we energize them to each winding, we provide by DC. So each time we have a so-called cos square, only a kind of square wave. So this square wave only have duty ratio for roughly about 2/3. And then the other 1/3, we don't need to do anything. So that's how basically the operation for this motor design. So here will be what it is. Then we inject the current for each of the phase. So like in here, we inject in here. When the motor rotate against the, say, North Pole, we energize the positive current. But when we rotate for 180 degrees, then that will become South Pole, we use negative current. So in this case, positive and positive, we also generate a positive back EMF in here. And then we have both negative, then we also generate the corresponding EMF. But later on, when we connect the two together, in this case, because of this negative manner, we are able to make it adding together become 2 positive. So that's how we arrange the 3-phase manner. So that every time the input voltage need to go through 2 of the winding plus the 2 back EMF here. These 2 back EMF must be arranged in a way so that these 2 voltage will adding together to against or to become the load, become the output for the DC source. So that's how the arrangement, we can make it these 2 voltage. When they connect together, they will add up these 2 voltage. So every time we only conduct for 120 degrees, and later on, then another phase will be conducting for another 100 and 120 degrees. So you can see that for each working time period, then we must have a 2 winding connected. For instance, this incoming positive, that will be negative. So in this case, we can one go into motor, one will come out from the motor in order to complete the loop of operation. So later on, we'll show the combination for all this to show you how and what method we're going to switch on the transistor. So you can also see that the back EMF, so we can inject current here by using our power electronics. But the back EMF are mainly produced by the induced EMF from the winding. So induced EMF from the winding mainly will come from the current interact with the permanent magnet. So the permanent magnet, you can see this here, we will have 120 degrees in here. And then you change over to another, this 120 will change over to the other pole when you rotate to the second half. So that will negative. So that means the back EMF will therefore become negative. So that's how we explain to them. Because every time they only conduct for 120 degrees, so then when they change over, this will have 60 degrees in here. So that's, you can see that in here we have this is 60 degrees, empty, we have nothing come out. But the North Pole, when we change from North Pole to South Pole, it won't change instantly, you change it linearly because this magnetic flux will therefore change over from north to south gradually. So in here, we assume the changeover will be linear change, but of course, it may not be exactly linear, maybe slightly curved. But even though we assume linear, then you can assume the back EMF, the magnetic flux will change from north to south, and then the back EMF will also change linearly in this way. Again, it may not be exactly linear, can be any shape, but we know that you're going to change from positive back EMF to negative EMF through that changeover. So this one of the phase we have, and then we, after delay by another 120, we excite another set of the phase, and also another set of phase, and following that. So that's how we make the switching cycle for the 3-phase system. this kind of brushless DC motor, we can have 120-degree phase, but we can also 4-phase and 5-phase, whatever. But 3-phase also really common. So that's how we get to the back EMF. So the input power in here, you can see the input power, when we have two negative here, then the input power, of course, will still become positive. So every time the motor will be arranged in such a way that you only draw the input power. So when both of them are positive or when both of them will be negative. So the way we drive the motor, in this example, I use the constant current to drive each winding. So because in this case, we just assume we are using constant torque to drive the motor. Constant torque will be one of the popular methods to do that. So that means, so if we use constant torque, then the current will be constant. So that's why you can see that when we excite this each of the phase current, this also will be more constant. So in this region, then we have constant torque operation for the motor. We can change the torque by changing the inject current, the IR current, or IB or IY. So the current input we all controlled by our power electronic. Next chapter will show you how we control the current. We can able to use power electronic to control amount of the current. But basically the current still more look like a DC. It look like DC, although we use p-time switching. It look like DC mainly because we are using high frequency switching, the ripple usually quite small. So that's why we don't have the problem of the a lot of some non-DC waveform in the current winding. So that's so the power level from that winding will be voltage multiplied by current, because as I mentioned, every time there will be at least two winding being excited. So that's why the total power will be multiplied by 2. Because you can see that from the operation here, then the current must be go inside winding and coming out from any one of the winding can be coming out from here. So every time there must be 2 winding in operation to complete the loop. So that's why when we look into the power, then we need to multiply by 2 because there at least 2 sets of the winding are being connected. So to model this kind of motor, we are using the conventional model method because the operations are very similar to a DC motor. So all the equations we use for DC motor can be against applied here. So let's define a number of symbols. Firstly, we define the resistance, copper winding resistance. Before we use RA, but now we use R phase because that's a per phase. Per phase means we have 3-phase motor there. Each of the phase have a 1 winding. So we measure this particular resistance for per phase. So that is to say, we measure this resistance. Then here we got Y connection here. So we just measure this path to see what kind of resistance. So for instance, that would be RA phase, RB, RY, red, yellow, and blue. So internally, there will be some resistance in the winding. So that's how we able to get that. And also each of phase, they have their own back EMF. So the back EMF will be red, yellow, and blue, 3 phases, their back EMF. So in this modeling, we assume the operation will be under steady state. Why is the under steady state? Then it just behave as DC motor. We don't consider the transient. When we transient mean when we changing the voltage, changing the current, changing the load torque. So we don't consider that. We just assume the motor has been run for quite a number of seconds and the torque speed will become stable. The power source here, we using power electronic to switch the power source from a DC power source to inject into each winding. The switching waveform later on will see you how they look like. Basically, they call it pulse width modulation. We are able to change the pulse width in order to obtain the necessary voltage inject to the motor. So we inject the current here, the switching current. Then the switching current, how we can change reverse the current direction. In the past, when we have commutator, we can reverse the direction. But now then what we need to do will be we can change the current. For instance, if these two are being turned on, voltage will be positive, right? But if we turn on these two instead, of course, we can reverse the voltage injected to the winding. So that shows you a simple way you're able to change the polarity for the input. So that was the basic method we can do. Okay? So in this diagram, I put the number here, 135246. So that is the switching pattern we will impress for each transistor. From using this switching pattern, 135246, if we turn on this transistor in this sequence, you are able to get how the motor will rotate from first time period, second and third one, continuously to rotate in such a manner. So that's pattern already written down, rather than you need to spend time to see which one to turn on, which one. So if you're using that switching pattern, we're able to obtain, that is how the waveform will look like. So we'll try to, for instance, for this case, we turn on transistor 1 and 6 and 1 and 2 and so on in this switching pattern. They happen to be these two with 1, 3, and 5. And then we have 2, 4, and 6. So that's how the pattern shall look like. So once we obtain this pattern, we are able to get this switching waveform. So in here, you can see that if we turn on in such a way, then the current can return to here, right? And then we can, once we do that, if we turn off this one, then we turn on that one, then of course then the current originally going to here, it will go through the diode. Yeah, so that's why we can able to use this method to control the current through each of the winding by using the switching mode method. So the operation basically discussed just now. So the switching pattern, I'd like you to go home to check about the switching sequence by using the numbering system here. And then if you consider in here 1, 6 turn on, which current to turn on. And then next, when we turn off number 6, turn on number 2 transistor, you can see how the current being changed over from one particular mesh loop to another mesh loop. So I need you to go home to try that, and then you can see how that switching pattern look like. Second thing will be we start to analyze the circuitry like what we did for the conventional DC motor. So this motor exactly the same DC motor, but instead we only use power electronics to do the switching instead. So that means the voltage equation is standard voltage equation. We got input voltage equal to the voltage drop on the resistor. That means the winding resistor plus the back EMF E. But because every time we got two sets of the winding, so the model here will be slightly different because every time the DC voltage minus the voltage drop for two transistors, ODS means on state. So when the transistor under on state, then you look like voltage drop. So for instance, in here, then you can see that in this loop, right, the current, every time you pass through two transistors, this transistor and this transistor. So that means the V here, after reduction for this and this transistor, you apply to the motor winding. So that's why you need to consider that is the on-state voltage from the transistor. So usually for bipolar transistor or IGBT transistor, the on-state voltage usually about 1 volt, 2 volt to 3 volt. So it won't increase so rapidly with the current. Some of them may increase rapidly, but for this kind of transistor like the IGBT or maybe MOSFET, it won't increase in such a way. And then we have two equivalent circuitry. We have two phase resistance. Because as you see that in here, every time when the loop is doing like that, then every time you pass through two resistors. And also, of course, the two voltage source in series, connected in series. Two voltage sources are connected in series. So that's exactly the same equation as before, but we modify all the components some of them will become double. And then the other equation, like the back EMF, like this equation, back EMF equation is unchanged. It's the same equation because it's the same concept. Even the torque also multiplied by current is the same concept. And then we can further modify to see, because every time we got two winding to operate, so eventually we can divide the equation to be the choice of the torque for each of the winding. So you can see that each winding, you have the same K constant multiplied by its own current. Yeah. And then we can also work out the proportional, this one, we can work out from the back EMF constant. Yeah, so they all tidy up really well. So in this case, we are able to work out the torque. Actually, will come out from two winding. Each winding contribute one torque. So totally, the torque will be multiplied by 2. Later on, we can see some equation how the torque equation related. So that's again that's a switching pattern. Then you can therefore in here we connect to the corresponding winding in this diagram. Then we can therefore create the suitable rotation. So pattern rotation, there's many different patterns. But here I already show you the pattern 1, 3, 5, 2, 4, 6. Then you can use this particular pattern to work out how the motor can rotate. So now then, that is the pattern we show you clearly. For instance, for that particular region, we turn on transistor 1 and 6. So when we turn on transistor 1 and transistor 6, conduct these two, we're expecting the current, therefore will go through in such a way. Yeah. So the current must be go through this way. And then we can also model the resistor. Two resistor must be being passed through. We can, because they connect in series, we can therefore using one resistor called R dash to represent them. The two back EMF, we can also using one voltage source because the torque constant will proportional to either one of voltage source. So we can use R E dash to represent two voltage source. And then after that, then the total equation will become this one. That means the back EMF, combine the back EMF, and also the current is in series, and the resistance will be individual resistance of their own winding. The next thing to do will be look into the torque and speed characteristic. You know, torque and speed characteristic for motor is so important. Before we can see the torque and speed characteristic, like the one we have before will be for industrial motor will be this one, right? So this region, we call it the constant torque region. The next region, we call it constant power. But in all this motor, we also call it field weakening because we need to weaken the field. The next thing to do, can we using this principle to see if we're able to sketch this constant torque, constant power figure, how they look like? Because we did that for the DC motor, right? We did that for the industrial motor. How about for brushless DC? Do you think they were the same? But the main difference for brushless DC compared to DC motor will be DC motor we can able to use the field winding. Conventional DC motor we can either use PM, which we cannot change the magnetic flux. But conventional DC motor we can use field winding, like those series winding and shunt winding, series parallel, or independent, separate, excited field winding, so we can control any magnetic flux. So in this case, we are able to achieve the torque and speed characteristic in such a way. That's a very common torque and speed characteristic. They all look like this manner. But now then, for this particular DC motor, brushless, how is this torque speed characteristic look like? Do we still have the constant torque region and constant power region? That's what we like to see. So that's two basic characteristics. We like to see what happened. So we have already done that. So this is the curve for the torque speed characteristic. So spend a little bit of time. Let's see how we understand that. So the speed here, we are increasing the speed in such a way. Then this is the back EMF curve E. We know that E is equal to K omega, right? That means the E is proportional to omega. So that means the slope here, the slope is equivalent to KE5, right? Oh, must be like that. Basic. So is a permanent magnet. So that means this is unchanged, this is a constant. So that means you can see that the slope here will be constant, linear increasing. And then so that is all back EMF, but the voltage here is equal to E dash plus the IR, right? The voltage drop on the resistor. So that means this is here, this is here, this one must be here, right? So the parallel curve represents the voltage drop on the resistor. When the current is constant, because we are using constant torque control, torque is constant, current will be constant. Yeah. So that is to say we are going to see this phenomenon. Oh, by the way, I haven't seen Cito for quite a few days. And Xiaodong, could you WhatsApp Cito to see is he coming?
Okay.
Yeah. I didn't see him for quite a few days. Because that's getting important. That's a really important DC bus motor. I want you all to understand properly. The important part is, although I record them in the Zoom, but to come here to listen to what I talk will be more important because I mentioned the most critical point. Zoom is not really clear because when I go away from the speaker, from the microphone, you can't hear anything in the Zoom. But I like to explain here so that you all understand how important this is really important curve for brushless DC motor. So that means this will be the back EMF triangular shape going up. This is a parallel curve to represent the voltage drop on the resistor, winding resistor. So that means this curve will represent the input voltage to the motor. Fair enough. So when you're using constant torque control, all the current torque will be constant up to this point. Tell me why we stop here, the torque start to decrease. Anybody can tell me why the torque start to decrease? We know the torque should be decreasing. No? In the constant induction motor, we know the torque also decreasing due to the field weakening. But we don't have field weakening here. We have the field will be fixed. But why the torque still decreasing? What happened?
Omega increasing?
Of course, the speed omega is represent the speed is increasing up to that base speed. Omega C called base speed here, or the critical speed here. Then we cannot maintain further of the current or further of the torque. Why is that? Why we can not do that? It's the same argument for all the motor. All the motor, when it go to the beyond the base frequency, we want to further increase the speed. Something happened to the motor. We cannot increase something further. That will be
Field weakening?
I'm sorry?
Field weakening concept like
we don't have field weakening here, right?
I mean the concept before we use them implement here, I mean the theory.
Before we have field weakening, we can weaken the field in order to further increase the back EMF, right? E equal to the back EMF equals to K phi omega, right? Back EMF. So in order to increase the speed, we can so before for DC motor, we have E equal to K phi omega. We increase this one, but E cannot be increased. It cannot increase. So only thing to do is to decrease the flux. So that's why we have that for DC motor. DC motor, right? But now then for here, the flux also cannot be changed, cannot change at all because we don't have separate winding, we have PN. So this cannot be changed. Now we want to increase this one. Impossible, right? Because E go to the limit. What is the E go to the limit? E is here. And then plus the voltage drop. So that's the input. So that is to say when we go to the input voltage for the motor, go to upper limit, that is the input voltage from the DC source. Maybe from the battery, but this source we can't increase further. Further increase this one. You see the E curve still going up if you further increase the speed. voltage, then it will still continue to increase. But what's the difference between these two? This is the voltage drop on the resistor. R cannot be decreased because there's a winding resistance. Voltage is limited. We cannot increase the voltage further because limited by the voltage rating for the motor, voltage rating from the inverter or the input battery. Voltage input cannot be changed. So this cannot be changed. This continues to increase. R cannot be changed. I have to decrease. The only thing we can do is decrease the I. Right? So this little triangle is mean the I is now decreasing. So until certain point when I becomes 0, we cannot decrease further. The whole system stop. So this point I is decreasing, that means I is proportional to the motor torque. The torque will decrease in a inversely proportional curve. So that's why the torque here will decrease with the increase of the speed or with the current. So that's why you can see that in this curve, the torque will decrease in a way that will be inversely proportional to the current. So when the current go up to here, this point, and current becomes 0, no more voltage drop in the resistor. I becomes 0, torque becomes 0. So that means the torque will stop in here, where the motor stopped. So that's how the Brushless DC motor look like. So the characteristic similar to induction motor or similar to conventional DC motor, but the torque equation will be different. This torque equation will linearly decreasing in a way to compensate for the dropping for the armature current or the motor current. For the induction motor, we have field weakening. So that means this curve, we are doing this proportional to the 1/omega. But now then we are doing linear. So in induction motor, this can go to infinity really low speed because it gradually proportional a bit. So in freewheel for induction motor or the other field weakening mode, we can increase to really high speed until the bearing, the shaft cannot, the mechanical cannot stand for such high speed. Otherwise, the motor can continue to go to really high speed. But for this kind of Brushless DC motor, we have limit here. That's it. So this period is very short, just a few further percentage, depend on the current. So that's how it look like. And then the DC equation is this one. So omega naught is the speed when it's going to stall. And then T naught is that particular maximum torque you can able to produce. I let you go home to derive this equation. This linear equation is able to derive it, and then you can tell me what is that T naught, what's omega naught, which show you the limitation for the speed for this particular motor. That is also part of our homework 5, maybe exam question to try to derive it. I think you can maybe be able to get it from the internet, but I'd like you to try it to understand it. Yes?
So what happens to the motor at omega naught or the last?
So for compared to which motor?
What happens to the motor at like the omega naught at the bottom? Yeah, here. What happens to the motor?
The motor you can see here, we have no more, the speed will drop to 0. And then the torque will also, the torque is dropped to 0. The speed is
0 at this point?
At this point, the torque equal to 0. So that means we cannot use the motor to sustain the friction. When motor rotate, even though we don't connect to anything to the motor, but we still have the friction from bearing, from that some other thing, that thing can be accounted for quite a few percent, maybe 10% or 5%. So at that point, we still need some torque to provide the friction. Probably at that point, the motor will stall. So that means when this little bit of the torque cannot supply to the friction, the motor will decrease the speed to 0. So at that point, the motor originally you had omega naught and maximum speed, theoretically maximum speed, but that means the motor will stall to 0. It dropped to 0, that's not moving. And then when the speed drop here, then you can probably go back to this point, and then continue to go back, and then probably fluctuating in this region. Okay, that's how the motor may happen. Of course, we don't like a motor to vibrate in between this region, so we need to control manner to control it so that we won't go to this region or won't approach to this region. So the best region will only appear in here. But this region we try to avoid. We can also operate in this region, but we need to control properly so that it won't go near to this portion of the road. Similar to the industrial motor, we tend to operate in the stable region, but we don't work in the really close to the zero crossing. That's a slightly, although stable, but the amount of torque will be so little. We try to work on more linear torque region of operation.
So is this region like harmful to the motor?
Yeah, I think this. So which region you think would be more comfortable? So
the
from
first
the
region
speed
will
control from this to here will be visually no problem because we can able to use the current control with many different ways to control the motor speed. At that region, is still able to work, but the torque become lower, low amount of torque. And then probably near this region, getting dangerous because the torque is not able to support the friction, windage loss, then the motor will stall. So how to do that? All the motor could be different because we don't know the windage loss, we don't know the frictional loss. So we need to do some pre-testing to make sure you won't go close to that particular region. Once you go to this region, the motor start to do some vibration, which we don't want to do that. So as I say here, it's your homework to derive this equation. Try to do that. We're going to assign the homework file later on, and then you got some time to prepare. And that's really important equation to show you how the brushless motor look like. So next, we'd like to show you another tutorial how the DC motor. The equation we used in this tutorial will be really similar to conventional DC motor. But here we just to show you the Y connection more look like a three-phase DC motor. So the question is, we have a PM brushless DC motor, and the torque constant will be equal to 0.12, and then they all refer to the primary side into DC supply size. And then we now need to estimate the low RPM. No low RPM, that means the torque current becomes zero, right? And then we supply with 48 volt. And part B will be if the armature resistance 0.15, we say per phase. We usually mean per phase. For three-phase motor, we are now using per phase. And the voltage drop for the transistor is 2 volt. Because that's a total voltage drop, so that means for the V on state will be equal to 1 volt, right? So how it look like. And then we need to determine the stored current and the stored torque. So next will be further on if say the DC current 8.2 amp, and then the motor now deliver 330 volt of mechanical output power. That's the real output power to the load with 3,400 RPM. So now then, again, we got 2 voltage drop, which means the V on state equal to 1 volt again. And then now there's star connection. So we do have friction will be this amount. So if the supply is 48 volt, we need to calculate the efficiency of the complete system. And then we need to determine work out all the portion as well. And then for the iron loss portion, we can use a parallel resistor to represent the equivalent core loss, because for all the iron loss, we can use a resistor to represent them. So this example shows you how the typical example for brushless DC motor. So let's see the solution. So firstly, we are asked to calculate the no load speed. When without any load, then that means I equal to 0. So the voltage drop here, IARA or the IRA will be equal to 0, right? So that means the total voltage 48 volt minus 2 volt from the transistor, VOC to VOC, and then divide by the torque constant. So the torque constant, the compounded torque constant is 0.12, right? So that means we got this RPM. That is the speed for the motor. Very simple, straightforward. The same as all the DC motor too.
It is 2 multiplied by KE pi, right?
Yeah, that's right, yeah.
So if you are 2 multiplied by 0.12, shouldn't be 0.24?
No, we have the compounded constant, the compound constant,
Oh,
or everything become compounded, yeah.
that is 2 KE pi
Yeah,
equal to
because we have each one will be K phi, but we have two of them. Yeah, because according to the torque equation, we combine them together, become 383. Yeah. And then the motor per phase resistance 0.15. And then we have 0.15, we have two of them in the Y connection. So that's why after the voltage drop divided by the resistor, then the current will be 153 amp. So that means the voltage at that condition will be 153 amp. So when this stands still, that means omega equal to 0. So it implies the E equal to 0. So we don't have the E in this equation. And then from the torque equation, again, we still using the same compounded constant. Then that's why we have the standstill torque. So that means that when the motor is standstill, the torque still there. We still have the standstill torque, which will be 18.4 Newton meter. So that's how you work out in the standstill condition. A and B are very similar to conventional DC motor anyway. But bear in mind, we are now using Y connection every time we got two phases of operation. So part 3 will be now we got 8.2 DC current that can deliver 330 watt and 3400 RPM. So the power, because we are using 48 watt input side, so the input power will therefore become 394 watt of power. And the power output will be this one. So that means these two ratios together, then we get the overall system efficiency to be 83.8%. So, and the next thing to see will be trying to get the iron loss, So iron loss in here will be, firstly, we need to calculate all the other possible loss in the system. We know the efficiency. Then we know between these two, we know all the losses. Some of the loss will go to conduction losses, some of them will go to other losses, but one of them will be core loss. So let's calculate all the losses, and then from there, we can work out the core losses. So for the transistor, we got this IDC current actually will pass through the transistor. Why is that? Because if you look at the way the operation, you can see that. So this DC current, you just flow through in this loop, right? So the transistor current equal to the input current anyway. This current will sometimes flow to here, return, every time pass through two transistors. Yeah. And then when this switch to this one, then this current will go to other transistor. So every time this current will go to any one of the two transistors in series. So that is to say, we will use this current to work out the transistor loss. Every time we have two transistors, because every time pass through two transistors in series. So that's the conduction loss for the transistor. For the winding as well, so we have per phase winding, and the I square R will be losses. You see, every time we have each winding, you have 2/3 of time being conducted. So you can see the curve again. So this is winding. So for the west phase, every time you have 2/3 of the time conducting. So that's why we multiply that by 2/3 here. We have 3 phases. So we multiply by 3 again, the red, yellow, blue, 3 phases. So that's the power loss for the winding. The vintage loss, we have vintage loss with the vintage torque, and then multiply by the omega, then we get the power losses. So these 3 are the 3 major losses for the system. So total will be 53 watt of the power. Fair enough. And then later on, just now we work out PE and PO 64. So the difference between these two, the remaining one must be the iron losses. So that means the iron loss will be 11 watt. So now that we got this loss, we want to make it equivalent to the RC, the iron loss resistance. So that will be something parallel with each of the phase. So that means the voltage, the input voltage here, because we have a Y connection, is DC, so this is VO, this is V dash. So each one of them will therefore become V dash over 2. So V square over 2, that's a phase voltage, right? And then V square over R is the losses. Each phase we got 2/3 of time being used, and multiply by 3 phase become 11. So now then we work out RC become 96 ohm. So that's a standard method how we can work out the core loss equivalent. So this example is very simple. Actually, the example for brushless DC and also for conventional DC motor are not much different. The only difference would be their Y connection. This example using the Y connection. As an advanced student, you may think about if the question taken into delta, how the answer will shall look like. There's also something quite challenging. Then you see for Y connection like this one, then you can see that the input voltage V dash share into V dash over 2. But if the motor is Y connection, the input V dash will equal to the V for this one, and then 2 winding will be shared by half, right? And then the loss calculation will be more complicated. You need to do more work out to see which voltage are shared by half, and even the current. If the current go into here, this current will split into 2, then you need to work out how the current being distributed. So this example, I use star connection slightly easier for you to understand the 3-phase brushless DC motor. But in case in some other operation, if we use delta, then it will be more complicated. You need to think about more carefully about how the current and voltage being distributed. So this chapter shows you a really basic principle for how a brushless DC motor look like. And I didn't say too much about it, but key thing here will be show you how to use power electronic circuitry, 3-phase inverter to work out this brushless DC motor. So the key conclusion here will be we try to turn the motor inside out. So by using this one, we're able to develop a new brushless DC motor. But all the switching are included in here so that we're able to replace all the brushes and commutation. So that's how to use power electronic to do that replacement. Before we don't have such a motor, I think 50 years ago, we don't have that motor. But since we have power electronic developed 50 years ago, we gradually move on to use power E to replace all the switching, all the commutator and common brushes. And then, however, this one, we need to observe the voltage position to turn on particular winding. So position sensor will be important. Without position sensor, we don't know where the position is. So we cannot energize the motor really fast. But however, you can see that for this motor, how are we going to implement a brushless DC motor without sensor? Do you think it's still possible?
No sensor?
Without sensor. We know this motor, we do need a sensor to sense the rotor position. That means where the PM is. But do you think we can do that without sensor? I think there's many sensorless control, right? Can we do that?
I think yes.
Yes, of course, yes. How to do that? Sensorless control. Although sensor control for brushless DC motor is not a new topic. It's a new topic 20 years ago, but not anymore. But just to argue how do we, what's the principle behind for the brushless DC motor without sensor?
The position by arranging the winding.
Arrange the winding?
No, by arranging what do you call it?
See how you have something to say? What?
I will say the brushless DC motor, the position is really important. So I just think about how can sensor this. So we need to use another way to get the position.
Yeah, another way to get the position.
Uh,
That's called the sensorless. Meaning all the motor, we do have a sensorless control. Industrial motor, DC motor, brushless DC motor, SRM, all the motor research paper, they have million of the brushless control one. It's a sensorless control. We have a lab like Xiaodong is working with a lab, so we can put the sensor without sensor. The motor still run, but of course, when we have sensorless, the estimate of the position may not be really accurate. The motor cannot run with really high speed because every time when we sense the speed, then if you don't sense it, then the position is not accurate. You can estimate position. We don't want to rotate the motor too fast. Rotate a slightly less speed, so we can able to estimate the position or not to estimate position. Just energize it. We thinking the motor rotate to here, and then we energize this winding, motor rotate to here. So we do it slowly. Instead, what happens when you develop the sensorless? When we do the lab, is the sensorless rotate slower or faster?
I think in the labs, the sensorless just open loop control. So we just energize windings by using the PWM frequency. But if we increase the frequency, the rotor cannot follow the magnetic field. So it is uncontrolled.
So instead, when you use without sensor, does the motor rotate slowly than before?
No change.
No change.
Yeah.
But when you load it up, then you cannot
Yeah, can
catch up.
vibration.
So that means once you load up, then the speed will be reduced. Then your final pulses cannot synchronize with the motor position. You have problem. For the sensorless control, we need to go back to this field diagram. Once we have the back EMF, where the back EMF come into will be when the rotor, the PM, near your winding. So that is to say, if you see this diagram, original diagram here, this PM, this PM, the PM are next to winding, you have the back EMF. And then if you do that, you sense the position, you sense the back EMF for this particular winding, you put the input here. And of course, you can know which one has back EMF. If the two adjacent phase has the back EMF, the rotor position must be there. So that's the way you can sense the position. You usually use the back EMF, sensing your back EMF to locate the rotor position. So quite straightforward. Of course, this method, you need to have more computational control. You need to have a more carefully control and then the feedback control. Many people, they don't like to have feedback control because sometimes sensor may not be accurate. Sensor may be broken, but the back EMF will not be broken. You're already there because that's the basic thing. We control the motor. So that's why I can see that in many of the computer, brushless cooling fans, they don't have sensor. Firstly, they reduce the cost. The whole effect sensor or position sensor is quite expensive compared to the motor. The motor only winding and PM, really low cost. But however, if you just sense the using controller to sense the back EMF, you can know the position really well. You don't need any sensor. So in this teaching, I said, oh, we need position feedback. This position feedback can be a sensor here, can be you detect the back EMF or other method. There's so many methods in the literature to detect the position. Anyway, so the conclusion in here, you can see that here, position sensor will be important because it has an eye to watch where the location is. And then we do need the inverter controller to do that. So we do all the switching. So the difference between this motor and compared to conventional DC motor, we can use pure DC to drive them. But this one you must use an inverter controller to do the job. So these two adding together will give you the whole structure, how we drive the motor. That's all. So this motor usually can have a high efficiency, mainly because we have less component, we don't have carbon brush, and commutator, all these things have a lot of conduction losses, and which we don't quite like. And then for high-speed maintenance, of course, brushless DC motor have a lot of advantages. But the driving here will be using cos squared. So next chapter, we're going to show you how to control the motor, how to control the kernel control to do that. But anyway, and so the basic concept for this brushless DC motor and conventional DC motor are quite similar. Principle are some similar. The control method, we can just share each of these two. So this one is a really good book from Tim Miller. He's one of the famous professors in UK, University of Aberdeen. So he written this book, and I think he also moved to Glasgow University, and so he would have time watch his book. Then he said quite a lot in the brushless motor and also reluctance motor too. I think he's really old now, probably had already retired. Anyway, so that's it.